Okay, everyone, let us conclude this unit talking about these four characteristics of waves: reflection, refraction, absorption, and diffraction. Let us begin by discussing reflection. What is wave reflection? Well, it involves a change in direction of waves when they bounce off of a barrier. Let us consider an example here. Let us imagine that we have a wall, and attached to this wall is a really long slinky. And imagine there's a guy off to the left here, and he's holding the slinky just like in the previous video. Now imagine that he gives a quick flick of his wrist, and he sends a pulse of energy traveling from left to right through the slinky, and that will look something like this. So the pulse of energy travels in this direction, and it bounces off the wall, and it comes back toward the guy. That's an example of reflection. Notice how the wave was traveling in this direction, and once it encountered this barrier here, it then changed directions and started moving in the opposite way. And notice that wave that was moving to the left, it was a mirror image of the wave that was moving toward the right, hence the name reflection. Let us now consider another real-world example of reflection, and this is something you all have experience with. How many of you all have been outside and you yell echo really loudly in order to hear your voice return back to you moments later? Well, that's an example of reflection. As you yell out, it turns out you send pulses of energy traveling outward in the form of sound waves. And so those sound waves then bounce off some barrier and start moving in the opposite direction back toward you. And the reason why you're able to hear yourself is because as you're sending out sound waves, you're creating pressure waves in the atmosphere. That's what sound is. It's pressure waves, changes in air pressure. And so as those air pressure waves bounce back and come towards your eardrum, it turns out they cause the air particles around you to vibrate. And those air particles then slam into your eardrum at a certain frequency, and so that's what you hear as sound. So in a nutshell, that's another example of reflection.
Okay, let us move on to talking about absorption. Absorption is when a wave comes in contact with the medium and causes the medium's molecules to vibrate and move. This vibration absorbs or takes some of the energy away from the wave. So here is an example of absorption. Imagine you're standing outside and you're looking at this pavement here, and you're wondering, why is it that the pavement appears to be black in color? Well, the reason why is because of absorption. Even though there's sunlight all around this pavement here, what's going on is that as the light comes in, so all these light waves, or in other words, electromagnetic waves, as those waves come in and strike the pavement, most of those waves are absorbed by the pavement. In other words, they are taken into the pavement and they are converted into other forms of energy, such as thermal energy. And of course, that causes the molecules in the pavement to vibrate faster, and that's why the pavement feels hotter. So that is an example of absorption. And again, it's the reason why the pavement is black. It's because what is blackness? Well, our brains interpret the absence of light as blackness. And so that's what's going on here. Most of the waves are absorbed by the pavement. They are not reflected toward your eyes, because if they were reflected toward your eyes, you would see something. But if since most of the waves are absorbed, you interpret that as blackness. Now, let us switch our focus to refraction. In physics, refraction is the change in direction of a wave passing from one medium to another. And here's an example of that. Guys, imagine here that you're standing and you're looking at this glass of water, and you wonder to yourself, why is it that the straw appears to be broken above the surface of the water? Well, the reason is because of refraction. What refraction is, it involves the bending of these waves. So, in other words, what's going on here is that as light waves come in and as they strike the surface of the water, they are changing mediums. They are transitioning from air to water, to a liquid. And so as they change mediums, they actually change the speed by which they propagate through the medium. And so that change in speed is what caused the waves to bend. And so this bending of the waves is what gives this appearance of brokenness at the surface. So that is refraction. And now the last thing I want to discuss in closing out this lesson is talking about diffraction. And in order to explain diffraction, I want to show you all a video from Mr. Anderson from the Bozeman Science Channel, because he does a really good job at explaining diffraction.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 110. It's on wave diffraction, which is the bending of waves as they move around an obstacle or through an opening. And so you can imagine these are water waves here moving from left to right, and this is an obstacle put in their path. And so as these ones on the top, they just keep going and going and going, but these ones right here are being diffracted. They're slightly bending around that obstacle. If we look down here, as they move through an opening, diffraction occurs as well. We're seeing that diffraction of these waves on this side. But there's not a lot of diffraction going on. And the reason why is the obstacle is much bigger than the wavelength. What happens if we make that obstacle or that opening the size of the wavelength or smaller? We get true diffraction. So what's happening is we're bending and we get these concentric circles that are moving out from there. Now, wave diffraction is going to occur if we have an opening for water waves like this, but all waves can be diffracted, even light. So if we put diffraction grating, small slits, we can actually diffract light and break it into its different constituent parts. And so wave diffraction occurs when we have either an obstacle or we have some kind of an opening. And as the waves hit the obstacle, they'll bend slightly around it. So an obstacle can diffract waves, and also a slit. So as it moves through, we're going to see a slight amount of diffraction as well. It's bending around that opening. But what happens if we take that slit and we make it the size of lambda, the size of the wavelength? What you get is true diffraction that's going to look like that. So what's an example of this? Let's say that you are here and somebody is talking in another room. Can you hear them talking? Yeah, and that's because the sound waves are relatively large. As they move through the door, they're going to be diffracted, so you can hear what they're saying. It might not be super loud, but you can still hear it. Now, can you see them around the corner if you're in a different room? No. Even though light can be diffracted, look at our opening. Our opening is so big compared to the wavelength of the light that it's not bending around that corner.
Okay, so we're going to pause the video there. Hopefully all of that made sense to you. If there's something that you need help with or you feel you need clarification on, please don't hesitate to contact anyone within the physics department. I hope you all have a good rest of your day, and I'm looking forward to hearing from you if you need me. Goodbye.